In this video, I'm going to show you how to calibrate the stretch of the bolt with actual load. What we have here is the same setup that I had before for torque angle measurement and load measurement. In here, what I have is the same fixture that holds the load cell and also torque angle transducer. We have a bolt here which has a sensor glued on it and attached to the load cell. And we have a tau transducer which transmits the ultrasonic information from the from the bolt to MC950. We're using this just as a transfer of the ultrasonic signal. We are not going to use the torque angle part of it, but since it makes it easier for us to do, we're using this. Also, we're going to use a wrench to do the tightening. It makes it easier just for demonstration. Here shows the bolt, which is parallel both sides and flat on both sides, and we have placed glued a utensile 2 sensor on the bolt. We push the tau forward until the pickup inside the socket touches the bolt. Now this is our setup, and as you see, the ultrasonic connection happens through here and goes into the US1, which is ultrasonic channel 1 on MC950. Here's another shot, shows the load has been connected to channel 2, analog 2, and torque angle is connected to channel 1. It's always easier to do it this way, and even if you don't use the torque angle transducer, it's better to set it up like this in case you don't use it. Then this is USB connection, it's connected to computer, and ultrasonic connection is connected to US1. Again, the same shot and above shot that shows you the connection that goes through load cell to channel 2. Now let's go and look at the software. So to start with ultrasonic, we go into use setups, and as usual, we start from left to right. There are tabs on top. Start with config logical channel. And, one is good for we're going to use only one ultrasonic channel. Then come down here and select, let's say, 3 bolts for testing. Then we go into the config bolts. We have 3 tabs. We need to put approximate length of the bolt, which is here is 2.2 inch. Since we're doing calibration, it really doesn't matter what we put on to the other tabs here, because it's going to be one quick shot. So we use echo 1, scan echo, that shows the echo that we're receiving from end of the bolt. Lock, 0 out, say echo, one after one. We just do it this way and click on calibrate. Shows up this window. Let's delete all that we have here. Okay, so in this window it shows the few parts of the first display would be the load, which shows load of the actual load cell, and time delay. These two are the most important part. You have to pay attention. Since we have a load cell, we need to calibrate load cell with MC950 as well. So if you haven't done it, you can do it here. Load input is channel 2, as I showed you, is connected to channel 2. So let's go click on check. We can read the sensor. So it reads the load cell, shows us it's a 100 kilonewton load cell. Transfer the data, transfers back to the actual calibration window. Click on calibrate and start cal. So this is done. You want make sure this is close to 0. So okay on both sides. So this has been calibrated. You only need to do once, then the calibration carries on for other bolts as well. And calibration time, let's put something like 7 seconds of calibration, and trigger at 1 kilonewton means once it reaches 1, it starts taking the data for 7 seconds, and pre-trigger is 10% of the time, which is 1.7 seconds allowed for before reaching the 1 kilonewton. So this makes sure that you have captured the whole load signal. To start with, start cal, we have a load close to 0, and we have time delay. Let's make it 0. So it makes a time delay. MC950 and US1 have two methods of detecting the time delay. One is a peak method and threshold. Most of the time we use the peak, but threshold is available. Let's just concentrate on peak. So now it's ready to go. Once it reaches 1 kilonewton, it will go for 7 seconds and will stop. I'm going to apply some load. Done. So what just happened, these are the load that we have collected. It has collected all the way to 28 kilonewton. And also these are the nanoseconds, which these are the time delays that have been captured. So there are 40 points, and also threshold has been captured. They are the same values. If the threshold has been set correctly, you should read the similar values. So to see the waveform, this is to see the calibration. That's what you have. 40 points. Your x-axis is your ultrasonic time delay, and y-axis is your kilonewton, which is your load. It's been applied. A polynomial is applied to this fifth order. It doesn't really matter what's applied here. We only looking at because the straight line we can always use 1. So it really doesn't matter what it is, because later on we're going to apply different polynomial. So this is for calibration. So it's okay. So we're done there. And since we have done this, we can apply all the parameters in here to higher bolts. We can go miscellaneous and copy bolt information. It's all the same. Copy, everything is in copy. Now, if I go to bolt number 2, I can do the same thing. And at this point, I need to change the bolt. So we will change the bolt. So we are using now another bolt. Scan it. Same record. We're going to see the same thing, and just another repeat. Same setup. We don't need to do much. Start cal. Zero it out. It's ready to go. Now we apply the load by torquing the bolt. Here again, the same, what we saw, same. And we change the bolt again, and then calibrate another one. It's usually a good idea to calibrate 3 to 5 bolts. More bolts, the better the results will be. The better average you get from all these bolts. So the same thing, bolt 3, scan echo, lock. Just continue on the same path and start cal. So I zero it out. Apply some load to it. So we have same information. So we have all 3 of them have been calibrated. As you see on these tabs, BL-LC means it's locked and calibrated. So we have 3 of them locked and calibrated. All 3 have their own calibrations. So what do we do with this? We have to come back and make an average calibration file for this. So using this information, you can go into the tools. Beforehand, it's a good idea to save all this information. To save, just click and give out the name. Let's give calibration. Let's call this M10 cal. It generates a UPF file, that's the ultrasonic project file. So let's go into the tools, create average load cal file. What it shows that we're using calibrated bolts from current logical channel. We have 3 bolts, bolt 1 to 3. You can select all 3. And we have here average of all 3 on top of each other. Because it was a similar bolt, you have similar information. But in the, it depends on bolt. Some bolts, they show different characteristics. But this one, because we're using very low the load, we come back to the same information. What we have calibration, and we have applied the polynomial order of 1, which is the straight line. So we can make average calibration file. We can give a name to this. It's called M10 cal. Then average cal. Calibration. What will happen? This will generate .cal file. So we already have a calibration file generated for this. These polynomials, you can change the polynomial as they change the curvature of the data changes. If you are going into the yield, you should use higher polynomials for this, 5th order preferably. Another method is interpolation. What happens? It uses all the data that's in it's available, so and it will not extend beyond it and beyond in the data collection, and beyond this it will put a straight line. So that's for interpolation. It means it would read the data on each point and interpolate between the points. And polynomial, it would extend some more beyond it, but it depends on what kind of data has been fed to this. So this is the polynomial interpolation method. So we can exit this. Now we have calibrated all 3. If you want to use this calibration file, let's generate another bolt. Let's say bolt 4. In this bolt 4, and now it's different. We can select our bolt type, and then we can load, let's say, use average calibration file. For this, we can open average calibration file. We won't just create it. That shows the file we just created. If I zoom it, there are 3 different calibration curves on this. So it shows you 3 bolts, and then also the coefficient C0, C1, that's offset, and slope of this line. If you have more coefficients, means you have selected higher orders, and that gives you the coefficient for those. So this is the calibration file you're going to be using for bolt 4. So if I continue on, and I have the same 2.2 bolt length, let me take this off. Suppose I use a new bolt on this. Now we want to measure the bolt on this bolt. Let's see, scan, lock, zoom out, save. In this time, we don't calibrate it. We want to use this is actual bolt in service. So I can click on monitor. Right now we are reading the bolt as reading the load as kilonewton, and is using A1, which is average calibration. 1 means polynomial 1. That is what we're reading at 0 at rest. If you see an offset, don't worry about this offset, because this is the result of the linear regression. So it selects the best straight line. If I start putting some load to this, this has stretched the bolt, and we just put 21.9 kilonewton on that bolt based on the average calibration file. So, and we also shows the 62.4, that's our delta time or time delay, either way. So peak, and this is the peak value and this is the threshold value. If I shift it, if I change it, the peak, as you see, the difference between the straight line is the peak value, the peak method, and the difference between, you can't see this one yet, is the threshold. So both of them are the same, you get the similar results. But majority of time, we just use the peak method.